In this unit, we will be learning about imaginary and complex numbers. Some quadratic equations have no real solution. For instance, the quadratic equation x squared plus 1 equals 0 has no real solution. Let's try to solve it. If we subtract 1 from both sides, we get x squared equals negative 1. And then if we take the square roots of both sides, x will equal plus or minus the square root of negative 1. And there is no square root of negative 1. There's no real number that can be squared to produce negative 1. Graphically, this can be seen by the graph y equals x squared plus 1. The parabola never crosses over the x-axis, so there are no roots of this function. To overcome this deficiency, mathematicians created an expanded system of numbers using the imaginary unit I. You have previously learned about rational numbers like integers, fractions, and terminating decimals. Irrational numbers like square roots of numbers that are not perfect squares, and pi. Now you will learn about non-real numbers, in this case, imaginary numbers. Imaginary numbers can be written with the imaginary unit I. So what is I? Well, I is the square root of negative 1. What can we do with I? Well, we can use I to combine imaginary numbers with real numbers in mathematical expressions called complex numbers. Then we can perform operations on these complex numbers, which many times yield real number answers. Here we have the square root of negative 4. Now 4 has a square root, but negative 4 does not. No number times itself equals negative 4. Using the imaginary unit, we can rewrite square root of negative 4 as square root of negative 1 times 4. Then we have two terms that have square roots, and the expression simplifies to 2i. Complex numbers are a mix between real and imaginary numbers. Each complex number can be written in the standard form a plus bi, with a and b being real numbers and I being the imaginary unit. Although a and b are both real numbers, only a is considered to be the real part of the complex number. bi is considered to be the imaginary part of the complex number, with b serving as the coefficient for the imaginary unit I. We can rewrite an expression like negative 5 plus the square root of negative 9 as a complex number in standard form. The negative 5 real part will stay as is, while the square root of negative 9 needs to be written in terms of the imaginary unit I. So the square root of negative 9 can be written as the square root of negative 1 times 9. And the square root of negative 1 is I, the imaginary unit. And the square root of 9 is 3, a real number. So this expression can be simplified into negative 5 plus 3i. The a is negative 5, the b is 3, and the imaginary part is after the 3. Now, any number can be written as a complex number. To write a real number as a complex number in standard form, you just add a 0i to the end of the real number. For example, 5 can be written as a complex number as 5 plus 0i. Like real numbers, complex numbers can be added, subtracted, multiplied, and divided. In order to add complex numbers, first add the real parts. A and C are the real parts of each of those complex numbers, and you can add them together as A plus C. Then you add the imaginary parts. BI and DI are the imaginary parts of the complex numbers. Adding them together is B plus D times I. Since I is the same in both of those, that is the imaginary unit, the square root of negative 1, I can be written on the outside of the parentheses. So let's see how this will work with 4 plus 7i plus 1 minus 6i. Well, first we will add our real parts together, 4 plus 1. And then we will add our imaginary parts. The b's, or the coefficients of the imaginary unit, 7 minus 6. And that answer times I. So 4 plus 1 is 5. 5 plus 7 minus 6 is 1. And we end up with 5 plus 1i, which also can be written as just simply 5 plus I. When subtracting complex numbers, first subtract the real parts, then add that to the difference of the imaginary parts. Here we have a plus bi minus c plus di. Well, a is going to be subtracted from c, as you can see here, and bi will be subtracted from ti, as you can see down here. Notice once again the I was factored out because I stands for the same thing in both of those terms. Another way to do it would be to distribute the minus sign between the two complex numbers to each the c and the di terms. We would end up with the exact same solution in this particular problem. So if we have the problem 1 plus 2i minus 4 plus 2i, I can take the real parts, 1 and 4, and subtract those, 1 minus 4, and add that to the difference of 2i and 2i. And I just wrote the i's on the inside, and that's okay too. So 2i minus 2i is 0i, and 1 minus 4 is negative 3. So that can be written as negative 3 plus 0i, but this is really a real number written as a complex number. If you have 0i, that means that you no longer have a complex number, now you have a real number. So that just equals negative 3. Here we have a larger subtracting complex numbers problem. And in this case, it actually makes a lot more sense to distribute the minus signs to the subsequent parentheses. So it says 3i minus, and then in parentheses, negative 2 plus 3i, which is a complex number in standard form. I am going to distribute the minus sign, make it a plus, and distribute it to the negative 2 and the 3i. It becomes a positive 2 and a negative 3i. And we will do the same thing with the second subtraction symbol. I will change it into a plus, and it will make this 2 negative, and it will make this 5i negative as well. And now we can rewrite this problem without parentheses. We're not worried about maintaining standard form because there's already a term in here that is not written in standard form, and that is the 3i at the beginning. So I'm going to rewrite these without the parentheses and with the correct signs now. So 3i plus 2 plus negative 3i plus negative 2 plus negative 5i. And one of the wonderful things is writing all the operations as addition signs is now we can move around the terms using the commutative property. So I can write 2 minus 2, just these two parts right here, those two real numbers, and add to that the 3i, the negative 3i, and the negative 5i. So 3i minus 3i minus 5i. And by simplifying 2 minus 2, which is 0, and 3i minus 3i, which is 0i, minus 5i is negative 5i. I can come up with my solution, which in this case, we can write it as just negative 5i. Or in standard form, we could have kept it as 0 plus negative 5i. Okay, now we move on to some of the fun parts, and that is powers of the imaginary unit. Now, this is important because you can use powers of the imaginary unit to eliminate imaginary numbers from your equations, leaving you with just real numbers and real solutions. So, how does that actually work out? Well, I to the first is just like I itself, and we know that I is the square root of -1. That's what I stands for. So I to the first is just I. Nothing incredible just happened there. But now let's look at I squared. I squared is the square root of -1 squared. And this is just fantastic because the opposite of taking a root is squaring something. So the square root of -1 squared is just -1. So if you have an imaginary number and somehow you can square that imaginary number, you will end up with a non-imaginary number. You will end up with a real number. -1 is a real number. So the key to turning imaginary numbers into real numbers is squaring them. But let's see what else we can do with them. I to the third. That is like the square root of -1 to the third power, which I could rewrite as the square root of -1 squared times the square root of -1, breaking it into I squared and I to the first. Well, we know that the square root of -1 squared, that first part right here, that just equals -1, but that will be multiplied by the square root of -1 like this. And what we end up with here is -1 times the square root of -1. That's like negative I. So if you have a positive I and you need a negative I, raise it to the third power. It will give you negative I. And I to the fourth, let's see, we have square root of -1 to the fourth. Well, I can break this up into two problems. Watch, I can break this up into the square root of -1 squared times square root of -1 squared. And I know that each of these is -1. Once we square this first part here, that becomes -1. Once we square the second part here, it becomes -1. And you multiply these together, -1 times -1, that equals +1. So not only do we know how to get an imaginary number to be a real number by squaring it, we also now know how to get it to be a positive whole number, a counting number, even 1. That's wonderful. We raise it to the fourth power and it becomes a whole number. Oh, that's great. What happens about I to the fifth? Well, I to the fifth would be I to the fourth times I to the first. So it would be I to the fourth. Let me write it. I to the fifth would be I to the fourth times I to the first. And we know I to the fourth is 1. And I to the first is I. It's just 1 times I. We're just right back to I again. I to the sixth, though, that would be I to the fourth times I squared, which would be 1 times -1, which is -1. So I to the sixth is the same as I squared. I to the seventh will be the same as I to the third. I to the eighth will be the same as I to the fourth. And it just keeps going through that rotation. Whereas if you get all the way up to like I to the 16th power, well, 16 goes evenly into 4, so that is 1. Or I to the 20th, that is also 1. Or I to the 18th, that would be the same as I squared, and it will be -1. Here's the same work done out just a little bit neater. It's important to note as these keep going up and up and up, they just keep recycling through the same 4 values. It goes I, -1, negative I, 1. Then the next one, I to the fifth, would be I, then -1, negative I, 1, and it keeps rotating through that indefinitely. So we are going to focus on powers of the imaginary unit I when we multiply complex numbers. First, we'll start off with a simpler one. This is 4 times -1 plus 3i, and you distribute just like we've always done before. In this case, I isn't a variable, but you almost treat it like a variable. It kind of is along for the ride, just like if that was -2 plus 3x. It will oftentimes do very similar things. The big difference is when you square it, know that it becomes a -1. So in this case, though, we don't have to worry about that. It will be 4 times negative 2 plus 4 times 3i. And that is negative 8 plus 12i. Very simple. Just 4 times negative 2 plus 3i. Now we have two binomials being multiplied by each other, though. Here it's going to get a little bit more complicated, but we've done this before. I am going to take this 2 and multiply it by the entire second parenthesis. So 2 times 4 plus 3i. And this minus, I'll make it a plus negative. And then I will multiply the I times the entire second parenthesis. So plus negative I times 4 plus 3i. Okay, we have some distribution to do here. So 2 times 4 is 8. 2 times 3i is 6i. Negative I times 4 is negative 4i. And negative I times 3i is plus negative 3i squared. So everything looks okay, but here's the first place we're going to see this. There's an I squared here, and I know that I squared really equals negative 1. So I'm going to substitute negative 1 for that negative 3i squared. So let me just rewrite that part. 8 plus 6i minus 4i minus 3 times negative 1. So now we don't have an I squared anymore, but we just have a negative 1. We can multiply that by 3 to get that to be positive 3. So let me let me add together the real numbers first. So 8 plus 3, that will be our real part. And that will be plus 6i minus 4i. That's our imaginary part. And from that, I get 11 plus 2i. And that's our final answer in standard form. Not bad. Okay, let's move on. Here we have another example of multiplying complex numbers. This one is going to give us a very interesting result, though. So I have 3 plus 2i times 3 minus 2i. So those look very similar. The only difference is the middle operation. One is a addition sign and one is a subtraction sign. Okay, so let me multiply them. So 3 times 3 minus 2i plus 2i times 3 minus 2i. And we distribute. 3 times 3 is 9, minus 3 times 2 is 6i, plus 6i, minus 2i times 2i is 4i squared. And now we know that 4i squared is really the I squared part. I can just substitute that with a negative 1. So 9 minus 6i plus 6i minus 4 times negative 1. Okay, so 9. And then minus 6i plus 6i, those will cancel. That equals 0i. And then we have a negative 4 times a negative 1. That's positive 4. So 9 plus 4, that equals 13. We started off with two complex numbers, and what we end up with is one real number, 13. We could write it as a complex number plus 0i if we wanted to, but there's really no need. We can just keep that as a real number, 13. And that's really good. When we have complex numbers, most of what we're trying to do is make them not complex numbers anymore, make them real numbers. And one way you do that is by multiplying two numbers that are going to cancel out all of the i's in that. These are called complex conjugates. They're numbers that when multiplied by each other, give you a real number solution. So let's talk some more about that. So a plus bi and a minus bi are called complex conjugates. And remember, these are the numbers that when you multiply them together, the imaginary part of the complex number is eliminated and all you're left with is a real number. It eliminates the imaginary part of the number. So complex conjugates are very important. And let's see how they actually end up working out. So by multiplying a plus bi times a minus bi, a gets multiplied by a, you're left with a squared. A gets multiplied by negative bi, you're left with negative abi, which sounds crazy, but it'll be gone soon. Then bi times a is positive abi, and bi times negative bi is negative b squared times I squared. So these two middle things are opposite of each other, so they just cancel out. And so those i's are gone. Then this I squared at the end becomes a negative 1. We write that down here. So it becomes a squared minus b squared times negative 1, which is a squared plus b squared. The negative 1 times the negative b squared gives you a positive b squared. So a squared plus b squared. That's good because a and b, you remember, those are real numbers. bi is an imaginary part, but a and b themselves are real numbers. So it becomes the real number squared plus another real number squared, which will give you a real number in return. So a plus bi times a minus bi equals a squared plus b squared. So the way these complex conjugates work are they are exactly the same a and exactly the same b. The only difference is the sign between a and b. So the complex conjugate of 4 minus 3i is 4 plus 3i. Once again, the a is identical, and the b is identical. The only difference is the sign in between is opposite of each other. Okay, so 4 minus 3i times 4 plus 3i. So if we multiply these conjugates, we should get a real number answer. It should be a squared plus b squared. So it should be 16 plus 9. Let's see if we get there, though. Okay, so 4 times 4 plus 3i plus negative 3i times 4 plus 3i. And distributing that, we get 16 plus 12i plus negative 12i minus 9i squared. Okay, all right, so these will cancel if we add those together. And we're left with 16 minus 9i squared. I squared is negative 1. And negative 9 times negative 1 is positive 9, so 16 plus 9. Oh, just like I said, and that equals 25. So by multiplying these conjugates together, the imaginary part drops out, and we are left with just a real number. In this case, it's 25. Cool. So we've multiplied and we've used conjugates to multiply and saw what effect that had. We're also going to use them with dividing. And the way that works is there's an imaginary number, there's a complex number in the denominator of this fraction. And even though we can't really divide it out that much, we can't keep that there. You can't have an imaginary part in the denominator of a fraction. You can't even have a square root of an irrational number in the denominator of a fraction. You can't have like a non-real number in a fraction. So we're going to use the complex conjugate to eliminate this from the bottom and turn it into a real number on the bottom. So I'm going to multiply the entire fraction by the complex conjugate of 4 minus 2i, which is 4 plus 2i, over itself. Now, algebraically, this has the same effect of multiplying by 1 because anything over itself is just 1. But it should eliminate the imaginary part in the denominator. So here we go. On the top, we will have 2 times 4 plus 2i plus 3i times 4 plus 2i. And on the bottom, we will have 4 times 4 plus 2i plus negative 2i times 4 plus 2i. That'll be pretty good. Okay, multiplying everything out. 2 times 4, 2 times 2i, that equals 8 plus 4i, and 3i, and then 3i times 2i. So 3i times 4 is 12i, and 3i times 2i is 6i squared. And beneath that, we will have 4 times 4, which is 16, 4 times 2i, which is plus 8i, and negative 2i times 4, which is minus 8i, and negative 2i times 2i, which is minus 4i squared. Okay, all right, there's a lot we can do here. Seems to be a lot. We have 2 instances where we have I squared. We have an I squared there and an I squared there. All right. So our next step will be to change those into whole numbers, and in the meantime, we'll also combine like terms here. So in the numerator, we have 8 plus, and then 12 plus 4 is 16, 16i, plus 6 times negative 1, because that I square was negative 1. And that will be over 16, and 8i minus 8i, that cancels out, which is good, minus 4 times negative 1. Okay, 6 times negative 1 is negative 6, and negative 6 plus 8 is 2. We can combine those like terms. 2 plus 16i over 16 minus 4 times negative 1. So 16 plus 4, which is 20. Now, a lot of the time, people stop here. I am going to distribute the bottom to both of these. So it'll be 2 over 20 plus 16i over 20. And reducing that, it will become 1 over 10 plus 4i over 5 by reducing. And that's about as simple as I can make it. It's written, it is an imaginary number. It is written in standard form, and it looks great. We divided. Nice job, everyone. Okay, the next thing we're going to clear up, because it hasn't come up yet in math at this point, it's about the principal square root of a negative number. And this is going to keep you all from getting questions wrong and not knowing why they're wrong. If you're multiplying two negative square roots by each other, you can't just combine them underneath one radical. Now, we could do that with positive numbers, but if both of the numbers are negative, you can't combine them under the same radical. Once you have a negative square root, as in this, you can rewrite that as the square root of a times I. You have to remove that I first before you start combining it with other radicals. So the square root of negative 3 times the square root of negative 12 cannot be rewritten as the square root of negative 3 times negative 12. Let's see. If we kept going with that, we would have the square root of positive 36, which is just 6. And that is not true. None of that is true. Instead, if we have the square root of negative 3 times the square root of negative 12, we must, before we combine those radicals, we must rewrite them without negatives underneath the radical. So I will rewrite that as the square root of 3 times I times the square root of 12 times I. And now I can combine my radicals, but I will also be combining my i's. So this will be the square root of 3 times 12 times I squared. And 3 times 12 is 36. So it's the square root of 36 times, and then I squared, that is negative 1. So square root of 36 times negative 1, which is the same thing as saying 6 times negative 1, because the square root of 36 is 6, and 6 times negative 1 is negative 6. If we had done it the other way, remember, I crossed it out, but it was a positive 6, and that was the wrong sign. So the number would be right, the sign would be wrong. You wouldn't know why the sign is wrong. Here's the thing. Can't combine two radicals when they have negative numbers underneath. That's it. You have to rewrite it with an I. All right, let's do a couple more problems with this. Okay, this might be a little bit of review for you all. We have two square roots that are negative, but they can actually even be subtracted the way you see them because they aren't exactly the same radicals. We'd have to simplify them first. But before we do anything, the principal square root of a negative number means that you have to move the I out first. So the square root of 48 times I, and that I is not underneath that square root anymore, minus the square root of 27 times I. And the square root of 48 is 16 times 3. 16 has a square root. It's 4. So I am going to rewrite this as 4 times the square root of 3 times I. And the square root of 27, that's 9 times 3, which is 3 times the square root of 3. And the I exists still outside of it. Now we can actually subtract these from each other. 4 times the square root of 3 minus 3 times the square root of 3 is 1 times the square root of 3, or just the square root of 3, and then the i's are around for the journey, so the square root of 3 times I. Or you could write it the other way, like I times the square root of 3. It works that way too. Okay, now let's square negative 1 plus then the square root of negative 3. So the square root of negative 3, I'm not going to mess around with that until I rewrite it as in terms of I. So negative 1 plus the square root of 3I, and that will be squared. And that equals negative 1 plus the square root of 3I times itself, negative 1 plus the square root of 3I. Now, a lot of people will look at this and they'd want to distribute this squared to each of these terms, and you cannot do that because there is a plus sign in there. That is a very common mistake. So we cannot do that at all. Instead, all we can do is say negative 1 plus the square root of 3 times I times itself. There we go. So you write it out, and now we have to end up, distributing a whole bunch. And that's great. I love distributing. All right, I'm going to start on the next line. So negative 1 times negative 1 plus the square root of 3I plus the square root of 3I times negative 1 plus the square root of 3I. Okay, we do a little distribution here. That is negative 1 times 1, negative 1 is 1. Negative 1 times the square root of 3 times I is minus the square root of 3I. And then subtract that from the square root of 3 times I plus the square root of 3 times I squared. And we could definitely do some simplification here. We have some like terms like this, and if we're squaring all of this, that would eliminate the square root in front of 3, and then I squared is negative 1. So let me rewrite this. The 1 in front stays 1. The negative square root of 3 times I minus the square root of 3 times I becomes minus 2 times the square root of 3 times I. And square root of 3I squared is 3 times negative 1. 3 times negative 1 is negative 3. Negative 3 plus 1 is negative 2. Negative 2 minus 2 times the square root of 3 times I. And that's our final answer. All right, I need to write that neater, so here you go. Okay, let's talk about factoring quadratics. Now, you didn't think you were going to get away from this without doing some factoring, did you? We're not going to factor every quadratic. We're going to focus on the difference of two squares and the sum of two squares. So the difference of two squares is a review topic. If you have two perfect squares like a squared minus b squared, that actually can be factored as just a plus b times a minus b. So if we have 4x squared minus 16, well, my a squared in this case will be 4x squared. So if I'm going to solve that, I square root both sides. A would be the square root of 4x squared, which equals 2x. And my b squared will be 16. And so b equals the square root of 16, and that is 4. So now that I know what a is, 2x, and b is 4, I can fill out this equation up here, 2x plus 4 and 2x minus 4. And that is what 4x squared minus 16 factors into. So this is a factoring review of the difference of two squares, which has a special formula to solve for that. It only works when it's the difference of two squares, when the number and when the operation in between the a squared and the b squared is a negative. But with imaginary numbers, we can do the same thing for the sum of two squares, meaning there's a plus sign in between two perfect squares. So let's take a look at that. So like the formula for the difference of two squares, here we have the sum of two squares. And that means a squared plus b squared. And as long as a is a perfect square, the first part is a perfect square and the second part is a perfect square, you can use this formula to factor what you have. And it becomes a plus bi. Now there's an I because in order for this to work, they have to be imaginary factors. And the same thing over here, a minus bi. So let's say we have x squared plus 25. Now can we factor this? Well, x squared is a perfect square, it's x times x. And 25 is a perfect square, it's 5 times 5. So our a would be x. If a squared is x squared, a would be x, and our b would be 5, because 5 squared is 25. If b squared is 25, the square root of 25 is 5. So we can fill out this formula, x plus 5i, and then x minus 5i. And that is a factored form of x squared plus 25. We wouldn't be able to factor it any other way. Here's a neater version of that, showing exactly how a squared became a, which became x, and b squared became b, which became 5. So we have used factoring to solve equations, and I'm going to do that here, but here we have the sum of two squares. So we have x squared plus 4. And x squared is a perfect squared. It is x times x. And 4 is a perfect squared. It's 2 times 2. So our a will be, a squared is x squared. Take the square root of both sides. A will become x. Our b squared equals 4. Take the square root of both sides. Then b will equal 2. So a is x, b is 2. Let's use the formula. So it is a plus b I and a minus b I. And that will equal 0. So the first part, the x plus 2i equals 0. Here we're using the 0 product property. So x plus 2i equals 0. So x equals, if we subtract 2i from both sides, we'll get negative 2i. That's one solution. And the other solution for the 0 product property, x minus 2i equals 0. So now I'll add 2i to both sides. 2i plus 0 is 2i. X equals positive 2i. So x will equal negative 2i or positive 2i. Here we go. We just solved a quadratic with imaginary solutions. Pretty cool. Here's the same thing written out neater, thus far less interesting. Okay, another place where imaginary answers comes up quite frequently is using the quadratic formula. And as a quick reminder, if you put a quadratic in ax squared plus bx plus c equals 0 format, this formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, will give you the solutions for x. They will solve for x for you. And remember, this part right here, that is called the discriminant. And if that solution, b squared, if that expression b squared minus 4ac is a negative number, you are going to have an imaginary number inside of this because it will be the square root of that negative number. So a lot of these, as long as b squared is smaller than 4 times a times c, you're going to get a negative number. So this happens quite frequently. And let's work on it a little bit here, shall we? We have the problem x squared plus 5x plus 6. And we're going to use the quadratic formula. Oh, I should write that equals 0. And we're going to use the quadratic formula to solve this. So let's do that. First, my a term is a 1 because there's just like an imaginary 1 right there. Not imaginary, but that's a tough word to say in this unit, you know. There's a unwritten 1 there. My b is 5 and my c is 6. So I know what my a, my b, and my c are. I can plug them into that equation. So negative b, which is 5, plus or minus the square root of b squared, which is 5 squared, minus 4 times a, which is 1, times c, which is 6. All of that written over 2 times 1. And that equals negative 5 plus or minus the square root of 25 minus 4 times 1 times 6, which is 24. All over 2 times 1, which is 2. Ooh, this one, we are going to get a positive answer in the discriminant. So negative 5 plus or minus the square root of 1 over 2. And 1 does have a square root. It is the number 1. So that equals negative 5 plus or minus 1 over 2. Now you might be wondering, like, why is there a plus or minus in here? Well, the fundamental theorem of algebra basically says whatever your highest variable exponent is, that is how many solutions any problem in that will have. So here we're going to have 2 solutions. Now there could be 2 imaginary, 2 real solutions, or they could be repeated solutions, which are the same number, it just occurs twice. So like both of them be positive 2, for example, would be a repeated solution. But here we are going to have two real solutions. So negative 5 plus 1 over 2 is negative 4 over 2, which is negative 2, or negative 5 minus 1 over 2. Negative 5 minus 1 is negative 6. Negative 6 divided by 2 is negative 3. Our 2 solutions are negative 3 and negative 2. That's great. Now let's try one that does not have real number solutions. Excellent. We have 3x squared minus 2x plus 5. For the sake of filling out this format correctly, I will make that a plus negative. So my a is positive 3, b is negative 2, and c is positive 5. All right. So our quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, and I can fill this out with the numbers I have here. So it will be negative 2. Notice the double negatives because it's a negative in front in the formula, and then b itself is negative, so we kind of have a negative situation. And b is negative 2 squared minus 4 times a, which is 3, times c, which is 5. All over 2 times a, which is 2 times 3. Okay, well, on the outside we have a negative negative 2. That's just positive 2. Plus or minus, and then the square root of, let's see if I can do this. Negative 2 squared is 4. 4 minus 4 times 3 times 5. That is 4 minus 60. All over 2 times 3 is 6. 4 minus 60 is negative 56. Oh. Negative 56. We're going to have the square root of a negative number. Now remember, we can't, the first and best thing we can do here is take the I out first. So I'll rewrite that as 2 plus or minus the square root of 56 times I over 6. And we can simplify the square root of 56. We can't solve it. There is no real answer. Well, there is a real answer. There is no rational answer for the square root of 56. Instead, it is 2 plus or minus 2 times the square root of 14 times I over 6. And a lot of times you write the I with the coefficient of that radical. So we can do that. 2 plus or minus 2I times the square root of 14 over 6. Now we're not done simplifying everything. The 2 that was our b and the 2i and the 6 are all even numbers, so we can divide each of those by 2 and get our final solution, which is 1 plus or minus I times the square root of 14 all over 3. Just dividing each of those coefficients by 2. And I can write this as in standard form like this. And that incorporates both of the answers. If we add them, that's one answer. If we subtract them, that's the other answer. That's totally fine. We don't have to break it out into two totally separate expressions. And that's it. That's using the quadratic formula when the solution is a complex number. All right, let's practice some of these.